Hi everyone. Today we are going to have the final video lecture on this course because on Wednesday we are going to have another live session through Microsoft Teams where I'm going to solve more exercises on graphs. Okay. Friday is a holiday, and then on Monday I'm going to be available. We are going to have again live sessions for you to ask any question about the course. Okay, so this is the last video lecture, and then we meet again on Wednesday and on Monday to solve exercises and for you to ask questions about all the topics that we have studied. Okay. Also, please let me remind you that from the School of Computer Science, the head of the school is asking us to remind you that you should fill in the academical survey. Okay, so if you find uh, some minutes to do it, it would be great. Okay. And the topic of today's lecture is what we call planarity and coloring of graphs, okay? And it has to do with um, several different problems that may seem at first unrelated, but that appear in many different situations, in practical situations, and that have a very interesting relationship and some important solutions and applications. Okay, so let me start by telling you about several different problems that may not seem, as I've told you, related one to another and may not seem related to graphs. Okay, the first one of them is the famous Sudoku games, in which, as you know, you have to fill in the cells in this square with numbers um, with a constraint. You cannot use the same number twice inside one of the little squares or in one of the columns or in one of the rows. Okay, so for instance here, since we have already a 3, we cannot use another 3 in this square, or a 3 in this column, or a 3 in this row. Okay, and we need to use numbers from 1 to 9. Okay, so how could we state this problem in terms of graphs? Well, for instance, we could assign a vertex to each of the cells. Let me draw the cells for the first square here, for this square, and then we could connect them one to another. Okay, so I would write here, well, all the connections. I'm not going to do it because there are a lot of connections, but this would be like the um, K9 graph, the complete graph with 9 vertices. Okay, for this square I would draw another complete graph of 9 vertices. Each of the squares would have a complete graph of 9 vertices, and then I would connect all the vertices in the same column, all the vertices in the same row. Okay, and the idea is that I need to give assign a number to each of the vertex, or each of the vertices in the graph, with the constraint that those vertices that are connected by an edge cannot have exactly the same number. Okay, so this is the restriction that, well, all those vertices are connected because they come from this square here, and they cannot have the same number. All the vertices in a column are connected, so they cannot have the same number. All the vertices in a row are also connected, they cannot have the same number. Okay, so it's a problem of assigning numbers to vertices, with the restriction, the constraint that vertices that are connected cannot have the same number. Okay? Let's think about a different problem and see if we can find something in common to the previous problem. So imagine that we have to assign some kind of resource. For instance, in the figure here, we have several different radio stations. And the problem is that if you have radio stations that are close to each other, when you assign frequencies, they can not have the same frequency. Okay, the same frequency, because then you have a problem with noise from one um, radio station to the other. You have interferences from one station to the other. Okay, so those stations that are closer than a given number of kilometers cannot have the same number of frequency to emit their programs. Okay, so what we could do is to draw a graph in which each station is a vertex, and those stations that are closed and could have problems of interference from one to the other are connected by an edge. Okay, and then we have to assign numbers to those vertices, and those stations that are close together, that are connected to by an edge, cannot have the same number. Okay, so it's a different graph, but it's the same problem that we had with the Sudoku. We have to assign numbers to vertices such that two vertices that are connected cannot have the same number. Okay, this problem can be generalized to almost any problem of assigning resources. For instance, imagine that you have to assign classes to exams, and you cannot have, for instance, the same exam on or the same two different exams on the same class on the same day. Okay, so those exams that are on the same day, the exams would be vertices. Those exams that are on the same day would be connected, and then you assign numbers of classes to the vertices, and those that are connected are on the same day, so they cannot have the same class. Okay, so you impose the restriction that the numbers that you assign to vertices that are connected are not the same. Okay, so again, it's the same situation. Imagine, for instance, that you need to assign uh, uh, planes to pilots that have to drive the planes. Okay, then you can have a restriction, for instance, that different planes that have less than a number of hours between the takeoff of one and the other cannot be piloted by the same person. Then you can connect, assign vertices to the planes, connect those vertices that corresponds to planes that cannot be piloted by the same person, and then you assign pilots to the vertices, names, numbers of pilots to the vertices, and those vertices that are connected cannot be piloted by the same person. Okay, so again, we have a problem in which we have a graph we have some vertices connected, and we need to assign numbers to those vertices with the restriction that those vertices that are connected cannot have the same number. Okay, a similar problem is one that is very important to us, and that in fact our compilers need to solve every time that we compile a program. Because as you know, for instance, when you compile Java or C++ or whatever, you have to assign the location of the different variables in memory. And in particular, you need to assign registers in the CPU to the different variables. Okay, so for instance, if you have a microprocessor with 16 registers, you cannot have more than 16 variables at the same time in the microprocessor. And those registers are the fastest memory that you have. You can access the data there very quickly. So you would like all your variables to be in the registers close to the CPU all the time. Okay, so when you have a program, you can have different variables that are used in different parts of the program. For instance, here you see that we have variable A, which has a long live in the program, then B, which is has a shorter life, E, which has a shorter life, and C and D. Well, you can have many different variables. Okay, and imagine that you only have a limited number of registers. So what you want to do is to assign variables to be in registers as long as you need them for the program to execute. And what you can do is to um, assign vertices to each of the variables and connect those variables that have an overlap in their life ranges. Okay, so variables that are connected are those that are needed at the same time. And then you assign names or numbers of registers to each of the vertices with the constraint that those variables, those vertices that are connected, cannot have the same number, cannot be in the same register at the same time, okay, because they have an overlap. Okay, so again, it's the same problem. This is a problem that is important, is useful for us as computer programmers, okay? A different program which seems a little bit more trivial, not so important, is the problem of coloring a map. Okay, so imagine that you have a map with different regions or different countries. For instance, we have here the different states of the United States. And you want to assign colors to each of the regions with the constraint that those regions that are adjacent cannot have the same color. This is, of course, for reasons of being able to distinguish one region from the next. Okay, so you want to assign colors to each of the regions with the constraint that those regions that are adjacent have different colors. Okay, so this problem again can be represented in a graph. You assign a vertex to each of the regions in the map, and you connect with edges those regions that are neighbors, those regions that are adjacent to each other. And then you assign colors, you assign numbers. For instance, 1 is color red, 2 is color blue, 3 is color green, or whatever. And then you assign those numbers to the different vertices, and you want that the vertices that are connected don't have the same number, don't have the same color, because they are regions that are adjacent. Okay, so again, it's the same problem. Again, it's the same problem, and you see that it can appear as well a problem that is almost trivial or just a fun game like in the Sudoku case, and it can appear as a problem of assigning resources, in which if you assign the radio stations or you assign the classes to the exams in a better way, you have a lower cost in your problem. Okay, so this is important because it can reduce the cost or the time that you need in order to take all the exams, or the number of frequencies that you need to use, or something like that. And it can also affect, for instance, situations in compiling or in the efficiency of programs. If we have the variables in the registers when we need them, the program will run faster. Okay, so this is a problem that can appear in many different disguises, in many different forms, and in some of them, the solution to the problem is important to us because it can help us making something quicker or with lower cost or something like that. Okay, so the origin of this story or of this problem is very interesting and is related to exactly the problem of coloring the map as the last example that I have showed you, and that is why this problem is called the coloring of graphs. And then we define a coloring of a graph as an assignment of numbers or colors. We can identify, as I've told you, 1 with red, 2 with blue, 3 with green. So an assignment of numbers can be thought as an assignment of colors. And then a coloring is an assignment of numbers to the vertices in a graph in such a way that those vertices that are adjacent do not have the same color. Okay? And we say that a graph is n-colorable if we can color the graph with at most n colors. Okay? If we have n colors at our disposal, then we can make a coloring of the graph with that number of colors. Okay? So for instance, if we have a triangle, it is clear that we cannot color this graph with just 2 numbers, because if we assign 1 to one of the vertices, 2 to another vertex, then the third one is connected to both the vertex that has number 1 and to the vertex that has number 2, and then it cannot have either number 1 or number 2, so you need 3 colors. Okay, so this is a 3 colorable graph, but it's not 2 colorable. Okay, and in general we are interested in what is the minimum number of colors that we need in order to color a graph. And that is what we call the chromatic number of the graph. Okay, so it's the minimum number of colors that we need in order to color the graph, in order to assign a different number to each of the vertices in the graph in such a way that adjacent vertices have different numbers, different colors. So here you have several different examples of graphs and their chromatic numbers. For instance, for this first graph, you can see that this is the K5 graph, the complete graph of 5 vertices, and in this case the number of colors that we need is 5, because each vertex is connected to all the others. That is the definition of a complete graph. So if I assign a number to one of the vertices, that number cannot be used in any of the other vertices because all of them are connected to the first one. Okay, so I need a different number to each of the for each of the vertices, and the number of colors is equal to the number of vertices. Here we have a different situation, which is a graph that is bipartite. Okay, and in that case, this is in fact the complete graph, the complete bipartite graph with 3 vertices in one side and 3 vertices in the other. And in any bipartite graph, we can color the different vertices with just 2 numbers, because I have 2 different parts, and the vertices in each of the parts are not connected among them. Okay, so the vertices in one part are not connected to any of the vertices in the same part, so I can assign the same number to that part, and then I can assign a different number to the other part. Okay, so I can always color a bipartite graph with 2 colors. Okay, here for instance we have a a cycle, another type of graph that we have studied. In this case, it's a cycle with 7 vertices. And in this case, I need 3 different colors, because if I start, for instance, here with color 1, then the vertices that are adjacent to each need to have color 2, and then I need to alternate color 1, color 2, color 1, color 2. And when I arrive at the last vertex, I notice that it is connected both to a vertex with color 2 and another one with color 1. Okay, so I need 3 different colors. If, for instance, I have, instead of a cycle with odd length, a cycle with even length, then I can color the graph with just 2 colors, because when I start with one vertex, then I alternate to number 2, then I alternate back to number 1, and so on. And when I reach the beginning, I will have a different number. I will have 2 instead of 1. Okay, so I can do it with 2 colors if the cycle is of even length. Okay, and in the general case, there is no easy way of finding the chromatic number. So here, for instance, you have 2 examples. Here the chromatic number is 4, and here again the chromatic number is 4. But to find that out, maybe you need to try many different possibilities. Okay, because finding the chromatic number of a graph is a problem that is very closely related to the kind of problems that we talked about when we were considering Hamiltonian paths. Because, for instance, deciding whether a graph is 3 colorable or not, if we can color it with 3 colors or not, is an NP complete problem. And you know that NP complete problems are difficult to solve. We don't know how to find the solution to that kind of problem quickly. But we can check the solution very quickly. If I give you an assignment of numbers to the different vertices of the graph, you can quickly check if it is a proper coloring, if it is correct in the sense that different vertices that are connected have different colors, and whether you use 3 or more colors. Okay, so checking whether an assignment of colors is a 3 coloring of a graph is simple. It's quickly. You can do it quickly. But in general, we do not know of algorithms that solve this problem quickly, and we strongly suspect that it's not possible to find an algorithm to solve the problem quickly. Okay, so again, this is a problem that appears naturally in many different situations, and is NP complete, and it's not easy to solve. We need some other way of trying to solve. What can we say then about the chromatic numbers of different graphs? Well, it's something similar to what we had in the case of Hamiltonian paths. If you remember, I told you that in general it's not easy to find Hamiltonian paths in graphs, or to check whether there is a Hamiltonian path in a graph or not. But for some families, it is possible to solve the problem quickly. For instance, if you have a tournament, you can always find quickly a Hamiltonian path. So the results that we have, or some of the easiest results that we have, there are many different research books and papers about the coloring problem, but some that are easy to understand and are related to things that we have studied are the ones that I present you here in this slide. The first one is something that, in fact, we have already mentioned today, and is the fact that a graph is too colorable if and only if it is bipartite. Because if it is bipartite, I have already told you that we can assign number 1 to all the vertices in one part of the graph, number 2 to all the vertices in the other part of the graph. And if the graph is too colorable, it means that I can assign numbers 1 to some vertices, number 2 to some other vertices, and the vertices with the same number are not connected. Okay? They cannot be connected because that is a coloring of the graph. And then I can divide the graph in two parts. The part of the vertices with number 1, the part of the vertices with number 2, and the vertices that are in the same part are not connected because they have the same number. Okay? And we already knew that this is equivalent to not containing cycles of odd length. Okay, remember that a bipartite graph is a graph that does not contain cycles of odd length. That is why in the first case that I showed you, when we had a triangle, we need 3 colors. Okay, we cannot color this graph with 2 colors because it has a cycle of length 3. Okay, so this is something that is very easy to prove, as you can see, and it can be useful in some situations. If I find a graph and I see that it is bipartite, I know that I can color it with two colors. If I know that the graph is too colorable, I know that it is bipartite. Okay. Another theorem that it's a bit more difficult to prove, but the idea is quite simple, relates the maximum number of colors with the degree of the vertices. Okay, and this is something that seems at least sensible because if I have a degree that is very big, it can mean that that vertex is connected to many other vertices, and then it seems that I am going to need many colors. Okay, this is not always the case. I will show you an example in a minute, but it can be an indication that the graph needs a lot of colors. Okay, so what we can prove is that um, if the degree of the vertices is at most d, then we can color the graph with at most d plus 1 colors. And the idea is not a complete proof, but the idea is that if I have a vertex that is connected to others, then I can assign here number 1 and then 2, 3, 4, 5 to avoid having vertices with the same color that are connected. It's not so easy as that. I need to do something a bit more clever than that. But the idea is that if I have a bound on the number of the maximum number of connections, then I can find a bound on the maximum number of colors. Okay, but this bound can be very bad. For instance, imagine that you have a graph like this one vertex that is connected to many other vertices. Okay, for instance, it is connected to 1000 vertices. Obviously, this graph can be colored with 2 colors because these vertices here are not connected to each other. So I can assign here 1 and then to all these vertices the number 2. Okay, and what the theorem is telling me is that, well, you will need at most 1001 colors. Yes, of course, because I only need 2. So this is giving me an upper bound, a maximum number that I'm going to need, but maybe it could be that I really need less than that number of colors. Okay, and there are other different theorems, other different results, but we are not going to study them here. If someone wants more information, just send me an email and I will be happy to oblige. Okay? Another problem that I want to talk to you about today that is related to graphs also comes from a kind of mathematical game. You see that in graph theory, many deep, profound problems initially came um, from mathematical games. For instance, the Königsberg Bridge problem, the problem of coloring a map. We will talk about that a little bit more later, okay? Or this problem of the houses and utilities. So imagine that we have three different houses, A, B, and C, and we want to connect them to the different supply factories, the one that supplies water, the one that supplies gas, and the one that supplies electricity. Okay, and we want to connect them with pipes and with cables on a plane, but in such a way that the lines, the cables, and the pipes do not cross. Okay, they cannot cross each other. So what we can do is to try and draw a graph with the three houses, the three factories or utility factories, and then we try to connect them somehow, okay? But without crossing lines. So maybe I can try something like this, something like that, something like this here. Then I can try to connect this here, but now I'm kind of running myself into a corner. It's not easy now to connect. I can connect these ones here, but then I cannot connect this one with this one. Okay, there is no easy way in this situation to try to find a connection without crossing the others. It can be mathematically proven that this is in general impossible. Okay, I cannot connect the three houses with the gas, water, and electricity facilities without crossing the lines, okay, if I do it on a plane. Of course, if I do it in three dimensions, it is very easy because I can do all the water connections at one level, then at a higher level the gas connections, and at a higher level the electricity connections. But if I want to do it on a plane, it can be mathematically proven that it is impossible, okay? And this gives rise to the concept of planar graphs. We say that a graph is planar if it can be drawn on the plane without their edges crossing at points that are not the vertices. Okay? So in the previous case, this is not a planar graph because there is no possibility of drawing the graph in a plane without crossing at least once the edges, okay, the lines. And notice that the graph that I was trying to draw here was K33, the complete graph with three vertices on one side and three vertices on the other, the bipartite complete graph. Okay, and it can be mathematically proven that K33 is not planar, not planar. There is no way in which you can draw K33 in a plane without crossing the edges at least once. Another graph that is not plane is K5. K5, the complete graph with 5 vertices. If you try to draw the graph without crossing lines somewhere, you will notice that it's not possible. You can try to do something like this, but then you again run into problems. This cannot be done. It can be mathematically proven that it is impossible. Okay, but K4, which is the previous complete graph, the one that is just below K5, is this one here. Okay, this is K4. And this is indeed a planar graph. This is planar because the definition of planar is that it can be drawn on the plane without the edges crossing. Okay? So in this form, the graph may seem not to be planar because the edges are crossing. But the definition of planarity is about the possibility of drawing the graph on a plane without the edges intersecting each other. And I can draw the same graph, for instance, in this way, or for instance, in this way. So I can draw the same graph. Remember that a graph is defined by the connections, not by the way in which it is drawn, but by the connections, by the adjacency matrix, if you want to think about it in that way. And then these three drawings here are of the same graph because the three of them have exactly the same connections. And if at least one of them has no intersections, then the graph is planar. Okay, so you must be careful because if I give you a graph and I ask you whether it is planar, you cannot resort on the way in which it was drawn. I can give you, for instance, this drawing here, and you may think that it is not planar, but if you can move somehow the edges to avoid the intersection, then the graph is planar. Okay? This is a problem that is important to us, also to computer scientists and programmers, because you know that the integrated circuits that we use in our motherboards, in our microprocessors, are planar. Okay, are located in a plane, and the different wires of the different elements cannot cross, because if you cross two wires, then you have a short circuit. Okay, and the the circuit is going to burn, is going to not work. Okay, so when you design integrated circuits, you have graphs, you have the different elements in the circuit, the different gates, the different uh, um, pieces of the circuit that you want to connect, and then you have wires. That is a graph, and the graph must be planar. If it is not planar, then you cannot print that circuit because it will short circuit. Okay, it is also related to problems of logistics, like for instance designing routes of different tracks or whatever, in which you don't want the tracks, the routes to cross. Okay, the routes in delivery service, for instance, you don't want your routes to be crossing because then you have a cost that is higher. Okay, then you need a graph that is planar. So planar graphs have been studied a lot, and it has been found that there is a solution to finding out when a graph is planar or not. So this may seem more complicated than the problem of, for instance, finding a Hamiltonian path or assigning colors to a graph, because well, you have to think about different ways of drawing the graph, and there can be many different ways. But there is a more or less simple way of finding out whether the graph is planar, or at least, if not a fast way, at least a way of um, characterizing when a graph is planar. And what it has been shown, what it has been proved, is that essentially there are some technical details, but essentially the the minimum planar graphs, non-planar graphs, are the ones that I have told you about, K5 and K33. If you have a graph that has K5 or K33, then the graph is not planar. And if your graph is not planar, then it is because it has something that is similar somehow in a mathematical formal way, that is similar to either K5 or K33. Okay? If somebody wants more information about this, what is the real theorem that can be proved, send me an email and I will give you more information. Okay? So we have these two different problems. The problem of planarity of graphs, the problem of colorings of graphs, and they are related one to each other in an interesting way. Okay? And this way has to be, this relation has also to do with a formula that you may have studied, for instance, in high school or something like that, and that was found by Euler, the same person, the same mathematician that solved the Königsberg-Pritch problem. So we started this unit on graphs with Euler, and we are going to end this unit also with Euler, with Euler's work. And this formula states that if you have a connected planar graph that is finite, well, we are always working with finite graphs, but well, the graph needs to be finite. If it is finite and connected, and you draw it in the plane without intersections, you can do it because the graph is planar. If you define V as the number of vertices, E as the number of edges, and F as the number of faces, which is the number of regions in which the plane is divided. For instance, if I have a square, okay, which is a planar graph, then I have two regions, this region here and this region number 2 outside. If I have another graph like this one here, then I have three regions, the two interior regions and the exterior region. Okay? And what Euler found out in relation to some figures, three-dimensional figures, like for instance the cube or the tetrahedron or the icosahedron, or this kind of regular polyhedra, what he found is that it always holds that the number of vertices minus the number of edges plus the number of faces is equal to 2. So for instance, here we have in this case that the number of faces is 3, the number of vertices is 4, and the number of edges is 5. And if you compute V, which is 4, minus E, we have minus 2, and then plus, minus 1, and if you then add F, which is the number of faces, you obtain 2. Okay? This holds also for the square, of course. Here we have that F is 2, V is 4, and E is also 4. So of course V minus E is 0 plus F, that is 2, is equal to 2. Okay, and this holds for any connected planar graph that is finite. Okay, this formula was essential to the study of a problem that relates the two concepts that we have been studying in this final lecture. the concept of planarity, and the concept of coloring. Okay, so if you remember, one of the problems that I stated at the beginning was how to color the different regions in a map without assigning equal colors to regions that were adjacent. Okay, and this was a problem that was discovered, let's say, in the 19th century, when some people began to think about what was the minimum or the maximum number of colors with which you could always color a map. Okay, so you have a map, and if I give you, let's say, 5 colors, can you color it? If I give you 4 colors, can you color it? If I give you 3 colors, can you color it? And it happened something similar to what happened with the problem of the Königsberg bridges. But this was a bit more complicated. Well, quite more complicated. So the history goes that some people were thinking about this, and in practice, it seemed that all the maps could be colored with at most 4 colors. There were maps that were not possible to be colored with 3 colors, but all the maps that were tried could be colored with at most 4. So then some mathematicians started to think about this problem. What was the maximum, the upper bound on the upper number of colors that you need in order to color a plane graph, a map? Okay, and this was discovered somehow by a mathematician called Guthrie, which told De Morgan about this problem. You know about De Morgan because of the famous De Morgan's laws. And De Morgan told Cayley, which was one of the top mathematicians of the time, and this was in 1852. Okay, so uh, people were beginning to think about this problem, and for several different years, for some years, nobody came with a solution. Okay, then in 1879 and in 1880, two mathematicians, Kemp and Tate, independently proved that 4 colors were enough to color any possible map. But their proofs were incorrect. There was a mistake in the proofs. These proofs were thought to be correct for about 10 years, and then Heawood found that the proofs were not correct. There was a mistake in the proofs, and what he was able to prove was the 5-color theorem, which says that any planar graph, any map, can be colored with at most 5 colors. But the mathematicians were not satisfied. They were not satisfied because, well, we have a theorem that says that with 5 colors we can color any map, but we have not found any map that cannot be colored with 4. Okay, so why cannot we prove that 4 colors are enough? Okay, why the best that we have been able to prove is just 5? Okay, and this problem stood for some time unresolved until in 1976 Appel and Haken were able to prove that we can show something better than the 5 colors that he would prove that were enough, because 4 colors are indeed enough to color any planar graph. Okay, so this is the connection, the deep connection between planarity and colorability. If you have a planar graph, then you can color it always with 4 colors. Okay, And this proof of this theorem, this is called the four-color theorem, obviously, was a bit problematic at the time because it was proved with the help of a computer. Okay, the problem here was that there were many different situations that needed to be studied, and Apple and Haken were able to, with mathematical techniques, reduce the complexity of the problem to a number of cases. Let's say several thousand different graphs that had to be proved that were four colorable. Okay, if they were able to prove that all those graphs were four colorable, then they could show that any planar graph was also four colorable. But the number of graphs that they had to try was very big, and it was impossible for a human to do it. So what they did was to contact some people at their university that were very good at computer programming. We are talking about 1976, where computers were not so common as today. It was not so easy to have a powerful computer. Most powerful computers were found in either companies or government facilities or universities, and they connected the computer science department of their university, and they uh, began programming computers in order to solve all those cases. And finally, they checked one by one with the computer all these different cases, and showed that indeed all planar graphs are four colorable. Okay, and this was problematic. There was some people that were not very convinced by this proof because by definition a proof is something that you can check. And if you don't had a computer, you didn't have a computer in that time, you could not check the solution. Okay, so it was in doubt whether this was a proof or not. Today, this is completely accepted. Well, on the one hand, because now we have computer power to try all these cases in just a few hours. Okay, it's not a problem anymore. And also because from 1976 to this day, computers have been used in many different mathematical proofs. So this is a tool that today is completely accepted by the mathematical community. Okay, in my own research, I have published solutions to problems in which we extensively use the computer to check different mathematical objects and to prove properties of this object. So this is something that is completely accepted today, and another way of proving theorems. Okay, so this story that I think it's very interesting and wraps up somehow all the different topics that we have been studying, and in particular in this lecture, can be found, for instance, in this book that I completely recommend to you, which is called Four Colors Suffice. It's very easy to read. There are a few mathematical formulas, but nothing that you cannot understand, and it tells the story of how this problem was solved. It's a book by Robin Wilson, and if you are interested in this kind of thing, I completely recommend it to you. And to finish up, my last slide is about a generalization of the four-color theorem that has also an interesting story. Okay, so this problem was, of course, initially stated for planar graphs. Okay, what is the number of colors that you need in order to color a planar graph? But you can draw graphs in other surfaces. You don't need to to draw the graph in a plane. You can draw the graph, for instance, in a sphere, or in a cylinder, or in a torus, or something like that. Okay, and mathematicians always like to generalize problems. So we have this four-color problem for the plane, but what is the equivalent problem? What is the number of colors that we need in order to color um, a graph that can be represented in a sphere without crossing the lines of the edges? Okay, so you can state this problem for any surface that you can imagine. Okay, and it was a conjecture by Heawood, the mathematician that proved the five-color theorem, and that found the mistake in the proofs by Kemp and Tate. He would conjecture that the number of colors that you need in order to color a graph that can be represented without crossing in a given surface, it's related to something that is called the Euler characteristic of the surface. And what is the Euler characteristic of the surface? Well, the Euler characteristic of the surface is the number that I obtain here if I take a graph that is possible to be represented in the surface without its edges crossing, and I count the number of vertices, I subtract the number of edges, and I add the number of faces. That is a number that is an invariant of the surface. Given a graph that can be represented in the surface without any crossing of the edges, if you compute this formula, you obtain always the same number. For the plane, this is 2. But for different surfaces, you can obtain different numbers. And that number is called the Euler characteristic of the surface. It has to do with the number of holes that the surface has some way. Okay, so for instance, a torus like this one here, this ring, this kind of ring here, has a different Euler characteristic. If you have something similar to that, but with two holes, then you have a different Euler characteristic, and so on. Okay, and what he would conjecture was that if you take that number and you plug it into this formula here, you obtain the number of colors that you need at most, in order to color a graph that can be represented in the surface without any crossing of the edges. And this formula, of course, works for the plane, because in the case of the plane, the Euler characteristic is 2. And if you substitute 2 here, you obtain 49 minus 48, which is 1. The square root of 1 is 1. 7 plus 1 is 8. Divided by 2 is 4. Okay, so this works for the plane. And in fact, this was proved in 1968, so 8 years before the plane case was solved, the four-color theorem was proved. This was proved in 1968 by Ringel and Jungs, except for the case of the plane. Okay, so this is a bit of a curiosity, because it was easier to prove the situation for all the rest of surfaces, with the exception of the plane. The initial problem was the hardest to solve. The mathematicians generalized this to other surfaces, and they were able to solve it earlier than the case of the original case, the case for the plane. And well, this is something that is, for me at least, a bit of a curiosity. Okay, And with this, I close up the lectures. Let me remind you once again that on Wednesday we are going to have a live session through Microsoft Teams. I will send you an email with the link and all that, in order to solve more exercises on graphs. Then on Friday we have a holiday, and on Monday we have the last class, and it's going to be again live for you to ask any questions that you may have. So thank you very much for your attention. As always, if you have any question, send me an email, or use the discussion forum to post the question. Thank you very much.